Hello everyone and very good afternoon all of you. I hope I'm properly audible to all. Let me know in question box in case I'm audible properly to all of you. You can also make use of chat box available over here as well uh, for the same. I hope my screen is also visible properly. Right. So yep, thank you for the confirmation and welcome all. So yesterday we sort of had some basic overview understanding of uh, data science and what exactly data science is about, and how we build up data science solutions and the project lifecycle of data science as well. Today we're going to be practically working with one of the example, and that's going to be the yesterday's data set, which is bank churn modeling. We're going to be loading that data, and we're going to be following some standard steps to achieve the intended result, wherein we wish to build a model, machine learning model, to train the model and uh, sort of make it possible to predict the customers are going to leave or not leave, like that, right? So that sort of stuff we're going to do with this, right, which is what we're going to achieve. So this is Jupyter notebook, which is what you're going to be using up. Okay, I'm going to name this out as the code as data science workshop code. Okay, and here we go. Okay, so yeah, that's what we're going to be doing up here. So there's a question: can you please define data science simply? We have discussed that yesterday in more detail. In a nutshell, if you want me to describe that, we can say data science is more about utilizing data to help enterprise to be able to solve some problem, or you can say use data, apply some mathematics and science on that to improve the business efficiency, right? For example, let's say that the problem statement here is, there's a bank, and the bank observed a problem that in last 6 months, a number of customers started leaving the bank. Now, this is a problem that the bank has. What I can do with data science is I can look at the data of all the customers who are leaving and who are not leaving the bank in last 6 months and identify on that data. I can apply some mathematics, some logic. What we can apply, we're going to see that today. By applying some mathematics, some logic, we can help bank to identify why people left the bank, what made customers leave the bank, right? So that sort of pattern we can identify. We can help them that, well, these are the reasons why customers left the bank in last 6 months. We can also use machine learning on the top of same data and build a model to be able to predict in future what will make customers leave the bank, or maybe in future which of the customers will leave the bank, right? So this is all about using mathematics, statistics, and machine learning on data to help business improve their business efficiency or solve some business problem. This whole segment is called as data science, right? So the segment where you make use of data. On the top of it, you apply stats or maths, and let's say stats and maths like linear algebra, statistics, probabilistic analysis, machine learning, and you build some solution which could help the bank or maybe any other business to improve their business efficiency or solve a problem. Is data science. I hope that gives you slight understanding. Bhavishna, let me know. Okay, so here we go. So yes, here we go. And so this is the problem you're going to solve here. So let's say that there's a bank. I'm describing the problem again. And bank has given us data of 10,000 customers, right? So we have data of 10,000 customers. As you can see that from 1 to 10,000, we have data. For every customer, we have row number of the customer. We have customer ID of that customer. We have surname of that customer, right? For every customer, we have row number, customer ID, and surname. We also have credit score of that particular customer. So for every customer, we have credit score, which is much more like CIBIL score between the range of 300 to 900. We also have geography of the customer. Customer is from France, is from Spain or Germany. We have gender of the customer. Is the customer female or the customer male? Right. We have age of the customers, right? So for every customer, we have the respective ages, tenure. That is how many years it's been the customer is associated with the bank. We have that as well, right? So that shows that customer is associated. For example, this customer is associated with the bank from last 2 years. This customer is associated with the bank from last 1 year, from last 8 years, from last 1 year, 2 year, 8 years, like that. The balance. What was the minimum balance reported in the customer's bank account in last 6 months? That is given to us, right? So these are the parameters we have. Next, we can see that we have number of products the customer has, right? So as many as product the customer has, maybe one product means only a single account, two products means a single account plus an insurance or a mortgage, right? So that could be, one feature. This feature shows customer has credit card or not. So one shows yes, customer has credit card, and zero shows no, customer doesn't have credit card, right? And next is it customer an active member, right? So that shows that uh, one shows yes, customer is an active member. That means customer has been doing some significant transactions in last 6 months. That shows customer is an active member. If customer has not been doing significant number of transactions, that means customer is not an active member. Right. Then we have finally estimated salary of the customer. What is the overall expected salary of the customer, right? That's we have. And based on whatever monthly deposit happening. And the last column shows the most important column, which is in last 6 months, the bank observed that a number of customers started leaving them. So this column shows 1, that means this customer left the bank. 0 means this customer didn't leave the bank. And this customer left the bank, this customer didn't leave the bank, this customer didn't leave the bank, and this customer left the bank. So last customer column shows that whether the customer left the bank or didn't leave the bank, right? So that's a label column. Our objective is to use this data first to identify what made people leave the bank, why were they customers leaving the bank. Secondly, use this data to build an ML model which can predict for a new customer whether that customer will leave or not. Right, so that's the idea so far. Are we good with this? Let me know if you have any question for the problem set, data set. Are we good with the problem statement? Okay, so I hope we're good with the problem statement so far. What we can do with the bank balance, it's just a parameter, right? Yeah, but it might show the the financial level of the customer. Maybe those customers who are financially very active might be leaving, or who are not active might not be leaving, like that. So it may have an impact, right? We might need to identify that. Okay, so I hope that answers the question. All right, let's go ahead, and for every column, we're going to be analyzing that out, whether that makes sense or not, whether is it important column or it is not important column. All right, so here we go. Let's get started with that. Okay, so we're going to be loading this data set, and for that, I will need to close this out, and we'll need to go to this option of sets, and maybe there I can simply go to ML, data set options, bank, and get here the bank chain modeling data, get the path. Okay, so first we can load some packets, import pandas, import numpy, import matplotlib dot pyplot as plt, and import cbon as SNS. These are the packages which you're going to use. First thing we're going to do is load the data. Right, so we're going to load the data as df equals to pandas dot read csv. So pandas is widely used for data import export, and also for cleaning and manipulation as well. But we can doing import export here. We'll print df dot shape to check how many rows and columns you are able to load. Then we look at df dot head to see that how many, the top 5 rows and columns to understand the data structure. Okay, there's a question. Can you provide the data set so that we can do the work parallel to you? Yeah, you can do that, and I can provide you the data set option. give me a moment. I'm gonna share you the link of it. Maybe this might not show you the screen for a moment. Okay, just give me a minute. I'm gonna share you the data asset bank churn modeling. So you get this link and can kind of yeah, save this. Yeah, you can't see the video. I understand that. I'm just kind of checking out the link so that I can share you the the data set. Okay, so let me put it here. So I'm going to send you the link. By clicking on it, you can access the dataset. You can go to file option and download the dataset as CSV file. Right. So I hope all of you would have received the link. Right. I'm going to put that again and say send to all. Right. So in case you want to do it parallelly, you can do that way. Come back here. So there's a question: what is the df.head is going to do? Well, so in cell number 2, we are trying to load the data. So df.head is going to help us out to see top 5 rows so that we can understand the data structure. So these are the top 5 rows we have. Right. I mean, with all the columns, as we can see: row number, customer ID, surname, credit score, geography, gender, age, tenure, balance, number of products, haircut card, is active member, and salary. We can also print this as well. In case you print that, you can see all the columns together here. Right. So this could be used to it's a CSV file. Database here is CSV file. Right. Okay. So you can see that all the columns over here were well mentioned. Okay. Now, let's say if I have to build a model, or maybe if I have to do analytics to identify what makes customers leave the bank, which of the columns out of these you think that should not at all be relevant, and you think that can be sort of dropped out, and we think that based on our logical understanding of banking domain, these parameter will not at all impact on the behavior of customers leaving, not leaving. Which of the columns you think may not have any relationship with customers leaving the bank or not leaving the bank? Cannot have any relationship, and you can reject that confidently by saying that, well, this column has no relationship whether the customer will leave or not leave. uh, Data science is not completely related to database management system. It is more related to using data and applying science on that, to infer more business logic. So data science is not related at all to database management. Database management is more of a engineering thing, and data science is more of a science thing. So engineering and science are two completely different things. Right. So first thing, there's a question: how do we find how many customers left? Well, we'll see that out, Bhavishna. But at this point of time, if we have to decide that, do we have such columns, you know, do we have such columns or parameters which will not have any relationship whether the customers are going to leave or not leave in this data set or not? Do you think that, do we have such columns which you can reject, and you feel that, well, this column doesn't make any sense whether customers are going to leave or they are not going to leave with respect to that, and may not have any pattern as well? Right. So I'm using Anaconda here. Right. So Anaconda is a Python distribution. So here we're using Python programming to do this job. Right. And let me make it a little bit more visible so that you can see the code as well. Okay. So well, I got an answer that, well, maybe row number doesn't make any sense. You can also look at this data as well, maybe the other way, and so here, if we have this data, which of the columns you think doesn't make any sense, and we should not consider that as a part of a research, that that doesn't make any sense whether customer is going to leave or not leave. So customer ID we have, row number we have, customer ID we have, surname of every customer, We have credit score of every customer. So out of these columns, which of the columns you think are not at all related and should not be considered as a part of research to identify whether the customer will leave or not leave? We have a number of products. We have estimated salary of every customer, whether the customer is active member or not, whether the customer has credit card or not, whether the customer has how many products. Right, so these are all columns that we have. So which of the columns you think may not be at all related and may not have any sense with respect to customers are going to leave or not going to leave? Right. So, Sri Harini, your questions are very different from the topic we're talking about. You see the difference between MySQL and Anaconda. Anaconda is a distribution of Python, which is a programming language, and SQL is a database management system. Database management is completely different to what data science is. Database management or SQL is used to hold the data or store the data, whereas data science uses data and uses some mathematics, and we use here some science or mathematics on the top of data to bring some relevant insights and results from the data, right? So SQL is used to store the data, whereas what we do in data science is we use the data and make some sense out of it, identify some insights or build ML model out of it, which is utilization of data. Anaconda is a distribution of Python, so we can do data science, implement data science using Python or R programming, any of these programming languages. Python is the one that we are using here, and Anaconda is a distribution of Python. If that gives you quite clarity about this. Okay, so yep. So the question here is that if I were to build an ML model on using this data, which is available in CSV file, right? If I have to build an ML model, machine learning model, right? And I have to use this data to train the machine learning algorithm, or else if I have to use this data to identify what makes customers leave the bank, which is nth column. So which of the column from A to M you think are not important, are not relevant at all to be able to predict the column N? Which of the columns you think that should not be considered as a part of a research to be able to predict nth column? So roll number, customer ID, and surname. At least we can say that if you talk about row number is just 1, 2, 3, 4, 5, 6, 7, 8, 9, has no pattern relationship whether the customer is going to leave or is not going to leave. So maybe row number can be dropped out, right? We think that we can say that row number doesn't make any sense about whether customer is going to leave or customer is not going to leave the bank. Second, if you look at customer ID is just an identifier like account number. So that also doesn't have any pattern. It should not have any pattern. It at all shouldn't have any pattern. So account number doesn't make any sense whether I'll leave the bank or I will stay with the bank, right? The same way customer ID doesn't make any sense, and it has no relation whether customer is going to leave or customer is not going to leave, right? Similar way, surname of customer should not have any relationship, right? So let's say what if we feed this data. So let's say there is a customer with my surname Pandey, and the customers with my surname are leaving the bank. And if you feed that data to the model might identify a pattern that all the people with surname Pandey are going to leave the bank, and the bank might start writing offers to them. So the idea is that if you feed wrong data to the model will learn wrong patterns. So it is very important to identify right set of data which has to be fed to the model. So I hope all of you agree that, well, maybe row number, customer ID, and surname should not at all be relevant whether customer is going to leave or not leave. Well, rest of the other columns, if you talk about credit score, it has to be statistically verified. We have to verify credit score, whether credit score is important or not. Geography, it may be possible in different countries. Customers may have different financial goals. And maybe they might be different competitor bank, which might lead to different geographical impacts, right? It may be possible that in different geographies, in different countries, there may be different competitor banks or government policies, government rules, which might lead to customers need different set of financial services, which might lead to customers leave or do not leave the bank. Male and female might have different financial goals. Balance, people with different higher or lower balance may have different financial levels. Higher balance people are rich, lower balance people may be poor, and they may have different impact. That might show different impact on whether they're going to leave the bank or not. So other features other than these three has to be statistically verified. That we can't just guess it, but we have to verify and prove it. So we'll see that how do we prove it. But at this point of time, can we say that these three initial columns, we can reject them based on our domain understanding, that row number, customer ID, and surname doesn't make any sense, has no relation whether customer is going to leave the bank or not. Let me know if you all agree. Do you agree that at least for these three columns, row number, credit score, and surname, we can reject these three columns and drop them out? That, well, these three columns doesn't make any sense with respect to whether the customer is going to leave or the customer is not going to leave the bank, right? So we can kind of drop them up, right? So that's what we're going to do, right? We're going to simply drop these three columns, considering that these three are not relevant. Okay, so let's do that and go ahead with it. So we're going to drop those columns. To drop them, we can write here, drop the unnecessary columns. So we'll say df dot drop the name of columns as row number, customer ID, surname, comma access equals 1, comma in place equals true. Right, so this is going to help them to drop them out. Let's look at df dot head again. So if you now look at df dot head, you see that those columns are not available, and we have sort of dropped them. How to join to CSV file and store them in one CSV file using Python. Akash, I can help you out with this solution at the end of the this problem statement. Okay, so well, at this point we have dropped this three columns, and now we have concrete data available. So you would want to go ahead and perform some analysis and computation on this data. So let's do that. So the very first analysis that we're going to do, right? So our objective is to identify how all these features are impacting the label exited. How is credit score important? Is it credit score important or not important? Is it having impact or not impact? Right? Is it geography having impact or not? Is it gender having impact or not? Is it age having impact or not? Is it tenure having impact or not? Is it balance having impact or not? So you want to identify for all these columns, is that these columns do have an impact on the customers leaving, not leaving, or not, right? Are these important columns? So should we consider them or shouldn't we consider them, like that, right? So there's a question, what is in place equal to true? So in that line number 5, x is equal 1 is for dropping a column. In place equal true is for permanently dropping that column from the data frame, not from the CSV file, but from the data frame that we have loaded. So in place true is like commit, is like if you want to permanently drop that, in place true. If you do not want to permanently drop them, you want to temporarily drop them, in place false. I hope that answers your question, Vijay. Okay, so x is equals to 1 is for dropping columns, and x is equal to 0 for dropping rows. X is equal to 1 for dropping columns, and x is equal to 0 for dropping rows. Yeah, the difference is that if you make in place false, those columns will not be permanently dropped. So for every execution you have to write this code. In every cell you will have to write this code for in place false. For in place true, once you have dropped them, they do not exist in your data, right? For example, let me show you an example, right? So let me remove this df.header from here. Okay, and again load the data, right? And I'm going to make this as in place false. Okay, and now you can see that there is no credit score, geography. I mean, there is no row number, customer ID, and surname. But if I load the data again, if I just check df.head again, I have row number, customer ID, and credit score. Sorry, row number, customer ID, and surname. But here when I drop this, it was not there. So in place false makes it temporary drop, and true makes it a permanent drop, right? So I'm going to make here in place as true, right? And put here df.head. So if I execute it again from beginning, so you can see that these are dropped. Again, if I check df.head, you can see that these are still dropped. They don't exist here, right? So that's how in place true is for permanent drop. Okay. Now, so you want to see the impact of credit score, geography, gender, age, tenure, balance, number of products, and these all columns, and how do they impact on the label exited, right? So we kind of want to see that impact and sort of understand, the how significant these columns are, for predicting whether the customer is going to leave or not leave, like that. Okay, so let's check out that. Right. So here we go. X is equals to 1 for dropping a column. In case you want to drop a row, X is equal to 0. In case you want to drop a column, X is equal to 1. Here we good. Right. Okay, so now we want to see the impact of, let's say, credit score versus exited. So how is that credit score impacting the people leaving bank, customers leaving the bank or not? Right. So for this analysis, we're going to be looking at a graph of probability distribution of credit score. Right. So we're going to be looking at a graph of probability distribution of credit score. Right. When customers are leaving, not leaving, we're going to compare the probability distribution to identify that is it credit score impacting the customers leaving the bank or not, right? So let's check that out here. All right, so plt dot figure, let's say fig size is 12 by 5. 12 is the width and 5 is the height of the figure, the graph you want to draw. SNS dot dist plot. So we'll draw the probability distribution of those customers who left the bank first. df of credit score, let's say we can say df dot credit score, and we'll write a condition that df dot exited is equal to 1. That means credit score of those customers who left the bank, right? So df of credit score, that means credit score of those customers for whom the exited column has value 1, right? plt dot show. So this is the probability distribution of those customers, probability distribution of credit score of those customers who left the bank. So x-axis here is showing credit score and y-axis is showing the density or the probability of customers leaving the bank at every value of credit score. X-axis is credit score, which is ranging from 300 to 900, right? So x-axis is credit score and y-axis is the density of customers leaving the bank at every value of credit score, right? So we can see that here there are less customers who are leaving the bank at lower value of credit score. So if I see that here, the customers who are leaving the bank at the credit score between 300 to 500 are lesser. In this range, there's less customers who are leaving the bank. There are less customers between 800 to 900 as well, not much, but majority of the customers who are leaving the bank are in this range. Majority of the customers who are leaving the bank are in this range, who are having credit score between somewhere around 500 to, or let's say 550 to 750. Okay, so there is a high density of customers who are leaving the bank in this particular range. Now this still doesn't give us complete answer about is it credit score impacting feature or not. So let's compare the credit score of customers who are not leaving as well. So what you can do is we're going to simply copy this and put it here and put exited equal to 0 and 1 and put plt dot legend 0 and then 1. So now we have two probability distributions. As we can see that we have two probability distributions. One is the distribution of those customers who are not leaving, and second is the distribution of those customers who are leaving the bank. So here 0 and 1 are the two probability distribution which are blue and red, right? So blue is the distribution of those customers who are not leaving, so that's representing 0, and red is the distribution of those customers who are leaving the bank. So as we can see that both the probability distributions are almost overlapping each other. Both the probability distributions are almost overlapping each other. So can we say that the meaning of both the probability distribution, both the graphs are almost overlapping each other? That means at every value of credit score, the density of people leaving the bank and not leaving the bank is almost same. Can we say that at every value of credit score, the density of people leaving the bank and not leaving the bank is almost same, right? As both the graphs are overlapping each other, that means at every value of credit score, the density of people leaving and density of people not leaving the bank is almost same. That means can we say credit score standalone doesn't impact the behavior of customers leaving, not leaving? As at every value of credit score, the density of customer leaving and not leaving is almost same. So can we say that credit score has no impact on the behavior of customer leaving, not leaving? Let me know if you all agree, right? As we can see that both the probability distributions are overlapping each other. That means x-axis, which is representing credit score, the probability distribution of customers leaving or not leaving the bank at every value of credit score is almost equal. That means the idea is that the credit score doesn't impact the behavior of customer leaving, not leaving. I hope I'm audible properly to all. Aditya, maybe there could be a challenge at your end. You kind of need to check that out. Right, looks like there's an issue at your end. Okay, so I hope you're good so far with that. Right, we can say that credit score doesn't impact as both the probability distributions are almost overlapping each other. Let me know if this is clear, and if you have any question on this, everyone. If it is not clear or any doubt that you have, right? Are we good so far? Legend is for that, plt.legend is that for this one. For this one, at the in the corner it is showing blue is for 0 and red is for 1. So legend is for that one. In the top right corner it is showing blue is for 0 and red is for 1. That is because of legend part. Fixed size 12 by 5 is what? 12 is the width and 5 is the height of the graph. 12 centimeter is the width and 5 centimeter is the height of the graph. The figure, the image. Excuse me. So 12 by 5 is the image size. Okay, hope you're good. Let's go further. Okay, so now let's say that we want to make a similar analysis for age versus exited. So I'm going to copy this code, and for code part you can drop an email maybe, or you can just drop in a request at contact@TechTrunk.in. So let's say instead of credit score we want to see the impact of age. Okay, we want to see an impact of age, and here we go. We'll say that here this is for age. So this is where we have drawn the probability distribution of customers leaving, not leaving at different values of age. Now let's say that So here we can see that on x-axis we have ages of all the customer, and y-axis showing the density of customers leaving, not leaving, at different value of age, right? In this case, the both probability distributions are not completely overlapping each other. They somewhat unoverlap, right? They somewhat unoverlap. Okay. Now that means if you try to analyze this unoverlap here, so if you look at this one, so can we say for age almost more than 40, you see, if you look at this, for age more than 40, there is a high density of customers of red graph, right? So red graph is having higher density compared to blue, right? For age more than 40, if you look at that, the red graph is having higher density compared to blue. So can we say that majority of the customers who are more than 40 years old are leaving the bank? Or for old age customers more than 40-year-old, there is a higher chance of customer leaving the bank, right? Can we say that customers who are more than 40 years old are having higher chances, right? So blue is decreasing and red is higher, the density of customers red graph, right? So the red graph is higher, higher density compared to blue graph is having higher density compared to blue graph. That means customers who are having, customers who are leaving has higher density value for people who are, having age more than 40 compared to not leaving. So can we say that majority of customers who are having age more than 40 are more likely to leave the bank? And if you look at the other way, this way, less than 40. For customers less than 40, there is a high density of blue graph, right? And that means majority of the customers who are less than 40 are less likely to leave the bank, right? So can we say majority of the old age customers are leaving the bank and young age customers are not leaving the bank? Let me know if you all agree on that. Can we say majority of old age customers are leaving and uh, young age customers are not leaving? Maybe the bank may not have relevant financial offerings to meet the financial goals of old age customers, right? I hope you agree with that. Okay, so that's idea so far about age part, and we can say that well. With this part, can we say that age is an impacting feature and credit score is not an impacting feature, right? Age is an impacting feature, credit score is not an impacting feature, right? Let's go ahead further. Now this is how we can do analysis for any continuous feature. Now let's say that we're going to shift to any different type of feature. We're going to do impact analysis of geography or gender, right? And see that how does that impacts, and how does that have analysis. So we're going to be looking at different other plots. So this could be probability distribution, probability density analysis could be one way to analyze impact of feature on the label, right? So we identified a pattern that, well, credit score doesn't have any sense about customers leaving, not leaving, but yes, it looks like the bank doesn't have relevant offers to meet the financial goals of old age customers, and that was one reason customers were leaving the bank. This is what we observe from the data. So this is what we call data science, observing pattern using data, using some science and mathematics on data to observe some pattern insights from it, and that can be helpful for the bank or any business to improve business efficiency. So these patterns that we are observing could be helpful for the bank, so that they can identify what are the loopholes or the drawbacks that they have in their services and where they need to make improvements. All right. So here we go. Next one, we're going to be doing analysis of geography versus geography versus exited. Right. So first, let's look at the geography of oral customers. That means the sort of plot of all the customers without putting a condition about exited, not exited. So simply PLT dot fixed size. There's a question: which type of mathematics is generally helpful? Probability and statistics. More of statistics and slightly of probability. Both are quite helpful. And then linear algebra. These three things are very helpful. First rank to probability statistics, second to probability, and third to linear algebra. Let's say this is something we're going to say 6 by 3 and SNS dot count plot df of geography, or maybe I can say that df dot plt dot show. So this is where we are not keeping any condition. We are not putting any condition about customer leaving, not leaving, nothing like that. Just looking at the graph of the the count of all the customers, irrespective they are leaving, not leaving. Right? We are not putting any condition about whether they are leaving, not leaving. Just looking at the graph of all the customers. Right? What you observe here is that if you look at the figure, so we are drawing the geography, and so it looks like that all the customers belong to three countries: France, Germany, and Spain. There are total 10,000 customers, out of which, if you look at France and y-axis, France has more than almost around 5,000 customers are from France. Germany and Spain, if you look at that on the level on y-axis, almost 2,500 customers are from Germany, and almost 2,500 customers are from Spain as well. Right? So France, Spain, and Germany are the three countries where all the customers of the bank belongs to. So you can say bank is operational into these three countries. And out of 10,000, 5,000 are customers are from France, 2,500 from Spain, and 2,500 from Germany. Right. So can we say that bank has good customer base, and you can say bank has good market in France compared to what it has in Spain and Germany by looking at this data. Now let's compare this with the data of those customers who left the bank. And then you have to make sense that which country has higher dropping rate. Right? So you can compare this graph with the data of those customers who left the bank. So I'm going to simply copy this, paste it here. In geography, put a condition df dot exited equal to 1. Simply put a condition. So we're comparing the total customers versus the customers who left the bank. And let's look at two graphs here. So first graph is for total customers, right? We can put a title here as well. Total customers versus customers who left the bank. Right, so total customers versus customers leaving the bank. So these are the two graphs we have: France, Spain, Germany, France, Spain, Germany, total customers versus customers leaving the bank. So what do you think? Which is that the three countries have similar dropping rate? If no, which of the country has higher dropping rate? So what do you observe out of this? Is that the three countries, there is the same dropping rate of customers in the three countries, or is there a different dropping rate in any of the country? If there is a different dropping rate, in which country or countries there is a higher dropping rate? Spain has no effect. In fact, France also has no effect. If you compare, the ratio of France and Spain is same, but the ratio of only Germany is high. You see, Germany has 5,000 customers, out of them 800 are leaving, which is same as Spain, 2,500 and 400 are leaving. So France and Spain has same ratio. Sorry, France has 5,000 customers and 800 are leaving. Spain had 2,500 customers and 400 are leaving, same rate. But Germany had only 2,500 customers and out of them 800 have left the bank. That means, can we say Germany had higher dropping rate compared to other two countries, right? That means maybe it is possible that age is impacting all the three countries, but Germany has some local challenges as well. That means for the customers of the current bank, whether there is a local competitor in the Germany which is causing the churning or attrition, or might have some different offerings which the current bank may not have, or maybe some government rules or regulations or policies in the Germany which might cause also the customer churn. So there are some local challenges as well in the Germany compared to the overall challenges, or some challenges or some issues with the customers only exist in Germany, which doesn't exist in France and Spain, right? So looks like geography is also an impacting feature. Well, let's do the same thing for gender. Let's do the same thing for gender. And you have to tell me, is that a gender impacting feature? So is there's a different impact for any gender group or not? So we're going to draw true graph same way. First graph is the total customer. Second graph is the customers who left the bank. So do you think both the gender groups have same ratio, or if there is any specific gender group which has higher dropping rate, then which is it? Right? If you think that there is any specific gender group which has higher dropping rate, then which is that? Okay, so looks like there were around 5,000 mails, more than 5,000 mails in total customers, but the customers leaving the mail are lesser, and there were lesser females, but the customers leaving the bank, higher females are there, right? So can we say females have higher dropping rate here? Okay, I hope all of you agree that. I hope you agree, Deepak. I hope you agree on that, right? Females have a higher dropping rate as well, right? So here we can see that females are higher dropping rate. That means the bank may not have relevant offerings or the bank's policies which might meet the financial goals of female customers, right? So that could be a challenge, right? So females also have, so gender is also seems to an impacting feature, right? I hope you're good with that, right? So next, let's say that similar way, if I do it for has credit card or not, right? So simply if we do it for has credit card or not, that's a column. So let's say has credit card or not. So total customers versus customers leaving the bank. Do you think that having credit card or not having credit card is impacting customers leaving, not leaving, or not impacting? You can also calculate the ratio as well. Right, having credit card or not having credit card, is that impacting customers leaving, not leaving, or has no impact on customers' behavior? Right. So as we can see that, for customers not leaving, let's say, sorry, for customers not having credit card, zero. There were total 3,000 customers, out of them 600 left the bank. So 1/5 ratio, right? So 1/5 ratio is there. 1 out of every 5 customers leaving. 3,000 to 600 is 1/5 ratio. Similarly, having credit card, 7,000 customers and 1,400 left the bank. Same 1/5 ratio. So can we see the same ratio is maintained for compared to total customers versus customers leaving the bank, right? So can we say having credit card, not having credit card is not impacting feature, right? So that's how, using multiple statistical analytics techniques, we can identify the features which are going to be important or uh, not important for the feeding into ML model. So this is what we do as a part of data analytics, right? We use data visualization, we use statistics, we use probability analysis to identify which of the data points are important or not important, or let's say what makes customer leave the bank, right? So this is what we do as a part of our data analytics process. Yeah, the code is simple. Df dot has credit card and has credit card. Df dot exit is equal to 1. So first graph is for total customers and second graph is for customers, uh, you know, uh, only leaving the bank. I hope we're good so far, everyone. Any questions that you have, let me know. Okay, I hope we're good so far. Go ahead. PLT, Matplotlib, and SCBON are the packages that we have imported earlier, right? So we can see that on the top. We imported matplotlib.pyplot as PLT, and we imported CBON as SNS. So Vijay, it will simply show the comparison with respect to customers who didn't leave the bank. But that's not our business objective. Our business objective is to identify what makes customer leave the bank, right? So exited equal to 0. Why customers are not leaving? If we make exited equal to 0, we will identify why customers are not leaving. Why customers are not leaving, that doesn't solve any business problem. The business problem is that a lot of customers have started leaving the bank. So we want to identify those reasons and solve those problems, right? So that's the reason if we use exited equal to 0, then also we'll get a graph, but that graph will not solve our business problem, is not in accordance to our business objective. Bhavishna, Seaborn and Matplotlib both are used for data visualization in Python. Both are packages for data visualization in Python. All right, are we good so far, everyone? Okay, I hope we're good. Okay, so here we go. Okay, so next part, let's say that now we have done some sort of analytics, and we also want to make use of some statistics as well. And so I'll just show you a quick idea of correlation analysis, which is also one of the very popular analysis done in data science, a statistical method, and there's a formula to calculate correlation between two things, right? So it's a statistical method and widely very popular for identifying an impact of a feature on the other, and we can use further to see overview impact as well, right? So let's understand the idea of correlation, what exactly correlation is, and how does that make sense? Okay, so here we go with looking at the idea of correlation analysis. So you see, when it comes to pattern, there can be two types of pattern: linear or non-linear, right? So like equations also are of type linear, non-linear. Same way, the patterns in the data can be also of type linear or non-linear. Okay, so let's look at an example here. So you can say that, well, this is, let's say, x and y, right? So we are simply looking at the idea of correlation analysis, right? We are looking at the idea of correlation analysis. Correlation is calculated between two features. Correlation is calculated between two features. And so I'll pin down here, calculated between two features, or you can say two attributes, which could be a feature in the label, can range between -1, -1 to +1, can range between, my minus sign of paint is not working out, so I'll have to write a pen here. So can range between -1 to, you can say, -1 to +1. Correlation can range between these two things, right? So we'll discuss about the pattern. Yep. And there's a formula to calculate it, right? So the formula looks like this. You can say the formula looks like this over here. If I have to write that out, you can say correlation between x and y can be calculated using the formula covariance of x and y, which is, let's say, 1 by n minus 1 summation of I equal to 1 to n x minus x bar into y minus y bar divided by standard deviation of x into standard deviation of y. That means 1 by n summation of x minus x bar square into 1 by n summation of y minus y bar square. That's a formula, but in Python we have a direct way to calculate that. Okay, so what exactly logically it makes sense? What sense it logically makes? That's important. So let's understand that. That two types of pattern, linear and non-linear. Correlation helps us out to identify linear pattern. So let's understand what kind of logic we can get from correlation. Okay, so let's say the data could be spread, in general, maybe in multiple methods or manner. So let's say if x, this is y and this is x, which could be opposite. Here I have written opposite, but yeah, it could be anyways. Okay, so data points are spread like this, let's say. In second case, maybe data points are spread like this. In third case, data points are like this. Okay, so in case one, can we say that for a lower value of x, there's a lower value of y. For a slightly higher value of x, there's a slightly higher value of y. So can we say, y increases as x increases? As x increases, y also increases, or if y increases, x also increases. Can we say like that? Right? So in this case, x is impacting y, or maybe y is impacting x, vice versa. Right? And in this case, whenever this situation exists, and you calculate correlation between x and y, correlation between x and y will be always a positive value. It will be quite closer to +1. Quite closer to +1. It will be very closer to +1. The correlation between x and y will be very closer to +1 if this situation exists. And mostly it is gonna be higher than +0.1 if this situation exists. In second situation, as you can see that for a lower value of y, there is a higher value of x. For a lower value of y, there is a higher value of, for a lower value of x, there is a higher value of y. That means y decreases as x increases. When this situation exists and you calculate correlation between x and y, it will be negative value. It will be very negative value, right? Maybe very much closer to -1. So this is also good correlation, and correlation between x and y in general is less than -0.1. So if the correlation in both the cases, case 1 and case 2, x is impacting y. So if the correlation between x and y is very positive value, it's a good correlation. If it is very negative value, it's a good correlation. In third situation, for a smaller value of y, there is smaller value of x, larger value of y, x. For larger value of y, also there is a smaller and larger value of x. So x and y are not impacting here, right? So you can see in this situation, if you calculate correlation, it's quite similar, closer to 0. Usually it is between -0.1 to +0.1. If the correlation is quite closer to 0, we say that x is not impacting y, or more precisely, x is not linearly impacting y. X has no linear relationship with y, right? So by looking at the value of correlation between the two features, we can, or two attributes, we can make sense how would be the possible impact. Is it like case 1 or case 2 or case 3? Case 1 and case 3, case 1 and case 2 are good impacting features, right? And case 3 is bad impact, or no impact, or no pattern, no relationship at all. Okay, so let's understand this. Let's understand this with respect to our data set. What do we observe as a part of correlation in our data set, right? So here we get to that. And as we already know the formula to calculate this, but here we don't need to apply formula. We just need to call correlation. It will do the job, right? So here we go and let's apply it. Okay, so we're gonna say that there's a question, I didn't understand the graph. Well, let me try it again. You see, in this case, can we say that for a lower value of, or let me, more precisely, let me kind of remove x and y here and change the place so that it'll be easy to understand. Okay, so let's say that this is x and this is y. This is y and this is x. Okay, so in this case, first case, can we say for a lower value of x, there is a lower value of y. As soon as x increases, higher value of x has a higher value of y as well. That means if x is increasing, that will also lead an increase in y, right? As soon as x increases, y will also increase. Similar case here, for a lower value of x, there is a higher value of y. As soon as x increases, but y is down. So as soon as x is increasing, y is decreasing out, right? That's the idea of, so in both the cases, there is a linear impact, but the direction of linear impact is different, right? So first case correlation is going to be positive, and second case correlation is going to be negative. If that makes it clear, Vijay, right? There's a question: is this workshop similar to the ML workshop? Well, not quite similar, but yeah, we're going to be looking at correlation. Might be quite a little common topic in both the cases, but yeah, the implementation is different here. So here we're going to be calculating that. So let's say correlation is we're going to be calculating as df dot correlation, and we're going to be looking at figure size at fixed size equals maybe let's say 10 by 10, and SNS dot heat map correlation matrix N naught equals true, and C map equals cool warm PLD dot show. So we got a correlation matrix here, right? And now we can make sense out of it, which feature is impacting, which is not impacting. In this matrix, it's gonna be let me actually make it 12, and this one may be 8. Okay, so this matrix is going to be symmetric matrix, right? Because correlation between x and y will always be equal to correlation between y and x, right? So lower triangle is exactly equal to the upper triangle. You can skip one of them. Diagonals are always going to be 1 because correlation between x and x is always going to be 1, right? So if you look at here, what we are interested into is the exited column, which is this one. With respect to credit score and exited, what is the correlation? Minus 0.027. So correlation between exited and credit score is what? Minus 0.027. So is it in which case? Case 1, 2, or 3? Minus 0.027. Is it similar to which case? Case 1, case 2, or case 3? You see the correlation between X and Y is minus 0.027. It's very closer to 0, isn't it? Minus 0.027, right? It is. So it is not case 2, it is rather case 3, because you see here, if you look at this one, let me kind of close this out. Just a moment. Today is 18 August. Okay, so if you look at this one, minus 0.027, and if you look at this drawing, we say that here it should be higher than 0.1, plus 0.1, and here it should be lower than minus 0.1, and here it should be closer to 0. So minus 0.027 is quite closer to 0. So can we say it is much more like case 3? Let me know if you agree. Correlation between X and Y is minus 0.027. So is it much more like case 3 here? Right? So that's where we can say that, well, looks like credit score has no impact on exited, which is what we also discussed earlier as well, right? Minus 0.027 is very closer to 0. That means no impact, right? We also discussed this earlier as well. Age, with respect to age, is it 0.29? So 0.29, is it similar to which case? Case 1, 2, or 3? 0.29 is similar to case 1, 2, or 3. Right? If you look at this, here the condition is it should be higher than 0.1 and lesser than minus 0.1, between minus 0.1 to plus 0.1. So can we say it is like case 1? That means as soon as age is increasing, chance of people leaving the bank is also increasing. Right? As soon as age is increasing, chance of people leaving the bank is also increasing. And we already seen that old age customers are more leaving the bank. The same pattern we observe here as well. Right? So 0.29 means what? Positive correlation. Positive correlation means what? As soon as age increases, exited chances also increases. That means those customers who have higher age have more chances of leaving the bank. We also observed this with probability distribution of data as well. The same pattern we earlier observed with probability distribution of data. Tenure. Is it impacting, not impacting? Minus 0.014. Case 1, 2, or 3. And then it is impacting or not impacting? Minus 0.014. So it's closer to 0, right? So not impacting. It's closer to 0. See, minus 0.014, lesser than minus 0.1. Sorry, lesser than plus 0.1 and higher than minus 0.1. So it's not impacting feature. It is between minus 0.1 to plus 0.1. Balance, higher than plus 0.1, impacting feature. Number of products, 0.048, closer to 0, not impacting. Has credit card, closer to 0, not impacting. Is active member, not closer to 0, it is far away from 0, impacting feature. Salary, not impacting feature, like that. So this is how we can sort of look at the correlation value and make some sense out of it, whether it is impacting or not impacting feature, by using this logic, this logic that we have seen here. If correlation between X and Y is higher than plus 0.1, that means first case exists. As soon as X is increasing, Y is increasing, that means X is impacting Y. Second case, where correlation is lesser than minus 0.1, in that case, X is increasing, Y is decreasing. X is still impacting Y. In third case, X and Y do not have any specific pattern relationship. And in that case, correlation is quite closer to 0, usually between minus 0.1 to plus 0.1. Okay, so that's how we can use correlation to to make some sort of analysis out of it. Okay, so then we are, so let's say that at this point we are kind of done with set of data here, and we think that, well, this is where we have done good value volume of analysis, and now we want to go ahead with ML model, right? So now we want to build a model to predict. So now you want to build a predictive model to predict. Okay, yeah, that was like this. This was the code. Okay, so first we'll separate X as, let's say, df of other than exited, we'll consider everything into X. We can drop credit score and has credit card because we think that those are not important feature, so we can drop them up. And Y is df of exited. So we have X and Y features and the label separately available. But if you look at X dot head, the feature X, we find that two features, geography and gender, are in string format, right? So these two features are in string format, and every predictive algorithm, which is ML algorithm, accepts data only in numeric format. So we can't feed this data as it is, right? We can't feed geography and gender as it is to the model. That's where we will need to do encoding of these columns. So whenever you get a feature in string format, it is very important that we do encoding of that particular feature, right? To encode this feature, we can simply load this feature and use an encoder from scikit-learn so that we can encode the string value into yeah, I didn't give in place because I don't want to drop exited permanently. I just want to drop exited temporarily and store into X. So X has that. So we are saying X is our complete features and Y is our label, the target which we want to achieve. So to the ML algorithm will feed the feature and the label, and it will learn from that. Right. So we are separating our features and the label, and then we'll train the ML model out of it. Okay. So well, that's sort of idea. Okay, we are not going to do validation analysis, but yeah, we're going to simply train the model and make a prediction out of it. Okay, so here we can see that one challenge is that geography and gender are in string format, so we need to encode that, right? So we'll encode the features, geography and gender. To do that, we'll import from sklearn dot preprocessing, import label encoder, and we can say le1 equals label encoder, and x of geography equals to le1 dot fit transform x of geography. Similarly, le2 is label encoder and we can say x of gender le2 dot fit transform x of gender, and let's say x dot head now. So we'll find that the features have got encoded now, right? So the feature is like the properties are features, the properties, the input data like geography, gender, age, salary, these are features, and the label, which the thing that we are trying to predict whether customer is going to leave or not leave, that column in the past data is the label, right? So we did encode it here. You can see that female, wherever there was female got converted to 0 and male got converted to 1. As there was no male, it was difficult to identify that. right? And in the geography, France got converted to 0, Spain got converted to 2, and Germany would have got converted to 1. So the values are assigned based on alphabetical order, FGS. So France 0, Germany 1, and Spain 2. Similarly, female 0 and male 1. Right? Based on alphabetical order, numeric values are assigned, and that's how the encoding is done. So we made our data, mathematically convert into numeric format. Now we're good to go ahead and train an ML model, and let's see that are we able to make a prediction or not, right? But this is not going to be a complete stuff. You can say there is a lot of optimization and tuning needed to this particular code that we can do, right? So now we will simply train a model, right? So from sklearn, we'll use an algorithm called logistic regression for this, which is one of the ML algorithm which is used for making prediction. Now there is some mathematics behind this algorithm, which will not be able to take at this point of time, but yeah, that's very interesting mathematics behind this algorithm. But yeah, and there are similar algorithms like neural networks, decision tree, and several other machines which can be used for building such predictive models, right? So we're going to be using one of them is which is logistic regression. There's a question why we encode gender and geography, because they were available in the string format. Every ML algorithm, if you have to develop predictive model, requires the data in numeric format. All other columns were in numeric, but these two columns are in string. That's the reason we are trying to encode them. I hope that answers your question, Pavishna. All right. So as these two columns are in string format, we are trying to encode them. Okay. So here we go. And now we are trying to build a machine learning model to do predictions here, right? So we'll write here logistic regression and train the model with the data, right? So we're going to simply train the model with the data. So for that, we can say that train the model with the data. So we'll say that model.fit x comma y. So the algorithm is going to learn from this data. We are with that. And once we are done with that, now we can go ahead and make a prediction. So at this point, you're done with developing a trained model. So let's say that we have a new customer, and for that new customer, we have to make a prediction. So let's say that we have a new customer, and that new customer is having credit score as 450, age as 35, and after age, which are the other columns? Uh, sorry, geography, gender, and then age, right? So geography is Germany, gender is female, age is this. Then tenure, balance, number of products. Tenure is 3 years, balance is this, and number of products equal to 3, and has credit card equal to 1. And let's say that we are talking about dummy customer here is active member equals to 0, and salary equals this one. And we want to make prediction whether this customer will leave the bank or not. Right, so let's create the array is equal to numpy dot array. We're gonna say credit score as 450, comma Germany as 1, comma female as 0, comma 35, comma 3, comma 564551, comma number of products as 3, comma is active member is 0, comma 456854. And you make a prediction for this, so we'll simply say the model.predict IP. So it's going to help us out with making predictions with that, and we're getting error here. Oh, I'm missing something. Okay, yes, has credit card. Okay. So this says 1. That means this customer will leave the bank. The model says that for this customer, the customer is going to leave the bank. If we tune some parameter to something else, so that we say is active member is 1, and maybe this is France. So this becomes sort of 0. And let's say that like this. And if you check that out, maybe the result might change a little. Not yet. Maybe I can say 25. And yeah, that could be one way, right? So at this point, it says that customer is going to leave, but yeah, in a lot of other scenarios, it might say that customer is okay. I didn't change it here. So when it is France, I have to make it 0, right? And female is 0, 25, and like that. And is active member, I have to say yes, active member, and also having yes credit card. Okay, so it says the customer is going to leave in multiple other scenarios as well. But yeah, we can tune the model, make it more accurate so that it will, give different result. Change age. Okay, I kind of made it 25. Let me make it sort of 15. So it says 0. Okay, that means customer is not going to leave. 20. Also it says 0. Customer is not going to leave. For more than 40, it's going to say customer is going to leave. So if I make it 60, so it's going to say the customer is going to leave. If I make it 20, it's going to say the customer is not going to leave. So it has learned those patterns. We have done the analysis of the data, but why didn't we drop those columns which are have no impact? Yeah, we should have done that. We should have done that, as we did not do very fine-tune analysis. That's the reason we didn't do that. So yeah, we should have dropped the credit score. We should have dropped has credit card or not. Right? So those columns could have been dropped out, and we could have got better results over here. All right. Okay, so that's sort of idea so far, and this is how we can build the model. There's a lot of other stuff as well. We can do validation and evaluation of model, whether it is good or not as well. So at TechTrunk, we have in case you want to dive into this stuff, we keep on organizing a lot of workshops like this and online trainings, and also the lot of similar uh, live training, self-paced courses. There are multiple such the courses that we organize at TechTrunk. So you can simply scroll to our website and look at self-learning courses, where we have video courses available on this to learn, dive deeper into these topics. And you can scroll through multiple courses. You can also get a lot of free courses as well, like robotics and Python are a lot of free courses. In case you're not aware of Python programming and you're not good at Python, you can go with these courses. And you can also get into live instructor-led courses taught online as well. And the built-in course is available. You can also inquire us for startup sorry you can also inquire for a coupon as well. We have a lot of coupons running up and discount offers, so you can connect to us for that as well. All right, so yeah, that's idea so far. Do we have to check each and every column, explore the data? Yes, Vijay, that's required. That's very important. And because in order to build a quality set of data, it's very important. Okay, so that's sort of idea so far. I hope you're good with that. You can look into our portal and get more details on that. So thank you all for joining the webinar today, and I hope you would have enjoyed it. And maybe you can catch out in any other workshop coming up. So thank you all, and good day.